everyone. So today we're going to find a series solution for y double prime minus 4xy prime plus 3y equals 0, centered at x equals 0. And so first of all, we're going to take on the expression y equals sigma going from 0 to infinity, cn x to the n here. Now, depending on where you're centered, if you're centered at another number than 0, let's call it that number c for a second. If it was centered at c, it would look like what I have here, sigma going from 0 to infinity, cn x minus c to the n. So in our case, it's x to the n. And what we're going to do is we're going to start by taking some derivatives here and eventually replacing these expressions with sigma into our differential equation. So you'll take y prime, which is, you basically use the power rule here. Put the n in front, subtract 1, you get what you see right here. And the index always goes up by 1 each time you take a derivative of a series here with positive or non-negative integers. So this goes up to 1. And then if you take another derivative, again using the power rule, this is the expression you get for y double prime. And what you'll do now is you'll replace the expressions with y double prime, y prime, and y with each of the expressions that we have here. And this is what you wound up with, okay? One thing to note here is I don't have a lot of time to show this, but this is what I would suggest you do, is to stop the video and notice how I got this notation. And I got that by, from here, replacing the y prime with what I had up here, and then minus 4x. All of that gives me what you see circled right there in orange, okay? So take a look at that for a minute. So I would pause this video just to see that. So we have our sigma notation here going in our series. Now, in order for you to proceed, the easiest thing to do here is to usually adjust the terms to a common power. And what I mean is have all the terms being this one, and this one raised to x to something. In this case, it's just, I think it's easier to x to the n. If anything common works, but x to the n is usually your best case here. And how do I do that? So the usual way of doing this is to replace n with n plus something in each of the terms that don't have x to the n. In our case, the only term that doesn't have x to the n is that x to the n minus 2 term, this first one right here, this whole thing. Okay, so we'll go ahead and do this. I'm going to replace n with n plus 2 everywhere in this notation here. And it's, why is it plus 2? Because n plus 2, if you replace the n here with n plus 2, you'd get n plus 2 minus 2. The 2's go away and just get n. And you just replace everything with an n plus 2, even the index right here, and you isolate the index to give you 0. So you have your series here. So that's good. And then what we're going to do is we're going to replace y double prime with that now. Okay. So we do that, you get this expression down here. Sorry, it's a little smaller here. I had to bunch up a couple things. Okay, and here's the issue now, among other things here. Your terms now don't start evenly. One starts at 0, one starts at 1, the other one starts at 0. You want them all to start up at the same value, okay? So as number 2 in red says, start all your terms at the same index by plugging in values of n from smallest value all the way up to the largest. So the idea here is you go and see what your largest value of n is that you start off with, which is n equals 1. So every one of these other indices needs to be n equals 1. Okay, and how do you do that? Well, you place n equals 0 in your expression, and you also will replace n equals 0 in your expression for this one and for this one right here. Sorry, that's what I meant to say down here. So you'll replace those with n equals 0, and you do that, this is what you get right here. So you should maybe pause the video for a second. So again, let me erase a couple things here to make things clear. And you will replace n equals 0 here and here. And this is what you would get. Get this right here. So you get 2c2 plus sigma plus minus 4 sigma, some stuff, plus 3c0. Sorry, there's an extra one here that shouldn't be there. plus 3C0 plus 3 sigma, etc. You should get something along those lines. And we're going to do a little bit more cleanup here. We're going to combine all the sigmas and everything else. So you get this expression right here, this plus this. And all of this at the end of the day equals 0. And all I did here was I basically got all the terms together, put the sigmas together into one single thing, and I got an x to the n. And well, because it's equal to 0 here, 0 is like saying 0 plus 0x plus 0x squared plus da 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 da. What does that imply? Well, it implies that 2c2 plus 3c0, that is the term that you have over here. All of that must equal 0 because that's a constant term on that left-hand side. So that constant term will equal 0. And then the other thing that you have is, well, because all the powers of x have to equal 0, that means all of this stuff next to x to the n inside the sigma has to equal 0 itself, okay? And what we're going to do with that is as follows now. So yeah, so there's a bit of work with these. What you're going to do is you're going to solve C for the highest term, C sub highest term, by setting the argument equal to 0 and solve for any coefficients equal to 0. So what I mean is we're going to actually solve for the highest value here that you see, C2, which was minus 3C0 over 2. And then what you're going to do is you're going to solve this expression for Cn plus 2. Cn plus 2 equals what you see here. And we're then going to work with what you have here. And we're going to find a pattern, if we can, from the recursion formula. If possible, we're plugging in values of the index. Yeah, that's the next thing. And that's actually one of the harder things here. Up to this point, it's just a lot of work. And if you follow these steps, you'll be good. The issue is when you're asked to find a pattern, okay? Now this formula begins at the one here with the recursion, n greater than or equal to 1. Okay, so please note that. So if you started plugging in values into that formula, if you plug in 1, you get C3, and that would equal what you see here. If you plug in n equals 2, you would have C4. But see, C4 is 5C2 over 4 times 3. We know what C2 is. We found that out. C2 is equal, my mistake here, minus 3C0 over 2. So what happened was that C2 over here was replaced with minus 3C0 over 3 times 2. And here's what I'm going to do. I'm not going to simplify these expressions. You might have seen that, hey, you can cancel a 3 here, which is true, but you do not want to do that. Trust me. You want to pick patterns up, and the best way to pick up a pattern is by not canceling things out. So essentially what you're going to do is you're going to go ahead and figure out more and more terms. Here's what C5 is, 9C3 over 5 times 4, but C3 is equal to C1 over 3 times 2, so we plug those in, and etc. C6. And the idea is, well, can I pick up on a pattern here? And usually it's going to be like the even ones have a pattern to them and the odd ones. So all the even ones look like you have a 2n factorial, okay? And you have on the even ones, if you notice the numbers you have, for example, C6, it's 13 times 5 times minus 3. So what does that mean here? Well, there's a difference of 8 for each of these terms. 13 minus 8 is 5, 5 minus 8 is negative 3. These all, and basically what this is forming is an arithmetic sequence. And that arithmetic sequence is 8n minus 11, okay? And what we usually do is we put a double factorial on an expression where you have the terms of an arithmetic sequence being multiplied out, like we do have here, okay? I will not go into how to find it. I'll just suggest you look up arithmetic sequences, not too bad. So that's what would happen. That's what the sequence would look like. And similarly, you have something for the odd terms, which would be this. Okay. Again, pause this video just to take a look at that. And when you get your series solution, the actual last one here, you're going to go ahead and say C0 plus C1x plus n equals 1 to infinity C2n x to the 2n plus n equals 1 to infinity C2n plus 1 x to the 2n plus 1. And the reason I split those up that way is because, yeah, there's patterns for the evens, there's patterns for the odds, and you just replace your odds and evens with your formula here. And yeah, essentially you can keep breaking this down. You can factor a C sub 0 and a C sub 1, and that's how I get that. Okay, so let me just do that out, just focus out on that, you can see. And yeah, you have two solutions, and that's what we would expect because we have a double prime here. And so basically that's how this works out. You start by taking some derivatives of your series, you plug them into your equation, make sure you get the common power of x to the n, make sure you get a common index, start point, and then you go ahead and try to solve for your recursion equation. And there you go. All right, well, thank you for your time.